All right, so 5:15. Okay, so I have that. It's essentially that time. Let me look at. Let me pull up 9 second. Okay, so we got 30 seconds. Let's see. I think we're streaming. Okay. All right. So we're gonna go ahead and get started, and we'll just be on the lookout for our brothers to get in. So let me see. As far as announcements go, so I spoke with the division chair, the mathematics division chair. Let me see. So yeah, after speaking with the division chair, so let me see. I'm under the impression that next Tuesday is our last. Well, the last official day that we meet with the students is next Wednesday. But so we're going to be done on next Tuesday, and then the week after that is going to be the final exam week. So I still have to. We're kind of waiting on an update as far as the final exam itself. So more than likely, it's not going to be on Pearson. There might be a common final. So we'll see. I have to give you some updates on that. So you have to hang tight on the final exam schedule for right now. Okay. Other than that, so today we're actually going to finish. We should be able to finish. We were with all my classes. We were able to finish the last of the lectures that I wanted to do. So we're going to finish out section 3.1 initially, and then from there we're going to go ahead. That'll be the last of the new material, and then for the remaining sections, we'll have about 4 sessions remaining: Thursday, Friday, Monday, Tuesday of next week. We'll use that time as review. Okay. So with that, we're just going to go ahead and pick up where we left off from section 3.1. Do you need to be rebooted? Probably. Okay. So let's do like this. Because I know sometimes you're temperamental. This one, right? This is the one. Let's let these brothers in. Okay. All right. So I'm just going to kind of move this to the bottom of the screen so I can see it as we progress. Okay. So we're just going to pick up where we left off. So it is election day. Hopefully you were able, if you are able to vote, hopefully you've already done that, and you're someplace safe to kind of make it through the night. With this purge. I mean, with this election, you know. No, exam 3 is not the final. Exam 3 is just exam 3. There's still another. Exam 3 should be available tonight. It should be available from tonight until Saturday. Right? Exam 3 is just exam 3. The final is going to be, so next Wednesday is the last day of class, so we're going to be done on next Tuesday. The following week, we're going to have a final exam somewhere during that time. I'm going to have to give you more information on the final. Okay? So picking up where we left off, so we're going to continue our discussions with exponentials, discussing compound interest. This is going to be the interest paid on both the principal and the accrued interest. Interest that is compounded annually is paid once a year. For interest compounded annually, the amount after 2 years is given by this. Right? So we have this example that says Juanita deposited $8,000 into a bank account at an interest rate of 6% compounded annually for 5 years. How much money will she have in her account after 5 years, and how much interest will she receive? Let me at least I can do this. That totally works for me. Okay, so I'm going to use a slightly different formula. So I'm going to use the compound interest formula. A equals P times 1 plus R over N to the power of NT, where N is going to be the number of compoundings per year, right? So the principal was $8,000. So she started the account with $8,000 times 1 plus the rate is 6%. 6%. Let me see right here. Mr. Let me go ahead and do this too because I think I'll forget if I don't do it now. And I'll just update them as they come in. Okay. So go back to this. We can let this student in. Okay. Let's see. So the rate is 6%. We have to express. So the Pearson work, you just want to get it submitted as soon as possible. Again, so our last class is next Wednesday. There might be a hard deadline of that Saturday night. The due date should be there. Keep in mind, more than likely we'll take the final, not next Wednesday. More than likely it'll be a week from this upcoming Wednesday. But just you have to kind of hold tight. Otherwise, you want to kind of get your Pearson stuff submitted as soon as possible. All right, that's the best plan of action. The due date should be next to each assignment, along with the hard deadline. Okay. Keep in mind that we have to submit grades, right? And I got to pull the grades from Pearson, so there's only so much further that we can go. We can't have it lingering. So you definitely want to go ahead and get Pearson in order. So again, when we use these formulas, the percent has to be expressed as a decimal. So if we have 6%, that's going to be 0.06 divided by, I think the interest is implied once per year, so the compoundings are 1. And the time is 5 years, right? So if we crunch that number, hey Siri, what's 8,000 times 1.06 to the power of 5? The answer is 10,705.8. And then for B, how much interest did she receive? So we're going to do basically the 10,000 minus her starting amount, which is the 8,000. So that's going to be 2705.80. That's how much interest is accrued on that account.
What does the N stand for in the equation?
N is going to be the number of compoundings, how many times the interest is applied in 1 year, right? That's actually right after this is right here, right? So this is the formula that I just used, was the compound interest formula, where A is going to be the amount in the account after T years, P is going to be the principal or the starting amount, R is going to be the annual interest rate expressed as a decimal. N is going to be the number of times the interest is compounded each year. So however many times we apply the interest in a year. And T is going to be the number of years, right? Let's see this more so in action. Okay. So say we have $100 and we deposit into a bank account that pays 5% annual interest. We're asked to find a future value after 1 year if the interest is compounded with these different compoundings, right? So for the first one, so the future amount, I'm just going to say A sub 1, because if we're doing it annually, that means we're applying the interest once in a year. The principal is $100 times 1 plus the rate is 5% as a decimal is this. This one, again, our N is 1 to the power of 1, and again, the number of compounders is 1, and the time is 1 year, all right? So then we crunch that number. I'm going to use a calculator. And actually, in each of these examples, it's all the same thing. The only thing that's changing is the number of compoundings in each example, right? So what I'm going to do is go to this y equals and type this in. So I'm going to say 100 times 1 plus 0.05 divided by, in this case, the compoundings are changing, so I'm going to say divided by x. Since the time is 1 year, again, the only thing that's changing are compoundings, right? So I just made a formula in terms of compoundings, okay? And let me go ahead and write everything out. So if it's semi-annually, that means we have two compoundings in a year, and the formula is going to be as follows. 0.05 divided by 2, essentially squared. Right? And then quarterly means that we have 4 compoundings per year. 1 plus 0.05 divided by 4 to the power of 4. Okay. If it's monthly, that means we have 12 compoundings in a year. And if it's daily, that means we have 365 compoundings. Okay. And let me let this student in and we'll crunch those numbers. Okay. So then now we put this function in the calculator based on compounding so we can crunch all of these numbers. I think the first one just ends up being 105. The second one, so I'll go to variables, y variables, 1 and 1. So when x was 1, when the interest was applied once in a year, we got a result of 105. So now let's say the interest was applied twice in a year, semi-annually. We get 105.06. Okay, say it was applied quarterly, 4 times in a year. 105.09. Say it was monthly. $105.12. And then say it was daily. So we applied the interest daily. 105.13. Okay. So it should be evident that the more compoundings we do, in a year, the more interest, the higher our return. Right? Okay. So again, I am monitoring the chat, and feel free to unmute yourself if you have questions. Okay. So then we saw several of this one work out, this compound interest formula, with several different compoundings in a year. Okay. So then we saw if we did if we applied the interest every day, this one is called continuous compound interest formula. Suppose we just continuously applied the interest on an account, right? So then that's where this one, I call it like A equals PERT. This is a continuous compound interest formula, where A is going to be the amount in the account after T years, P is going to be the principal, right? R is going to be the annual interest rate expressed as a decimal, and then T is going to be the number of years. E in this case is a function in the calculator, kind of like pi, right? It's similar to pi, but it's a function in the calculator. Okay. So we're asked to find the amount when the principal of 8,300 is invested at 7.5%, compounded continuously for 8 years and 3 months, right? So since we have continuous compounding, we're going to use the PERT formula, which is A equals P e to the RT, okay? So then the principal was 8,300 times E, the rate, 7.5% is going to be 0.075. And it says 8 years and 3 months. So that 3 months we need to convert to years. So 3 months divided by 12 months gives us 0.2, a quarter of a year, right? So this is going to be 8.25 years. And then we just crunch the number. Let's see, does T always equal years? Or, in general, the time, especially for like these interest formulas, the time has to be in years. Um, yeah, for these. Usually the time is in years. But we'll see some examples where it's not, and it's not really interest, but it's the same. It's a similar exponential function. But when we're doing interest, like compound interest and continuous compound interest, sorry, yeah, the time needs to be in years, right? Okay, let's keep going and see what happens. Oops, wrong swipe. So we just crunch that number. You just want to make sure that you can generate this number. It's a calculator point. Doesn't E mean 10? No, I think you might be confusing like E is a number. It's like 2.73 blah 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 blah. This is long decimal. Base 10 is like you might be thinking of like common log versus natural log, right? Some calculators they do put exp or e, that means the exponent, but in this context, they're talking about the inverse of the natural log. It's like if you did I think it's the compound interest formula where you start with $1 and you get 100% return, and you take the limit as there's a whole little thing. It's the limit as something as one of the terms goes to infinity. This formula approaches this number e. All you need to know for right now is that e is a function in the calculator. It's not power 10 in this case. All right. So let me show you what I mean. So let's hop over here. So right here, where you see natural log, this ln, e is right above it. So I guess we can go ahead and type this one in, right? So you can see it. So if we do 8,300 times e, so I'm gonna hit second natural log, e to the power of 0.075 times 8.25, we should get that 15,409.83. Okay. Yeah, these are good questions though. I'm gonna put this back here. Okay. So again, the natural exponential function e to the x. This is what we were kind of discussing. This is with base e is so prevalent in the sciences. It's often referred to as the exponential function or the natural exponential function. Right. Okay. So if we looked at the graph of y equals 2 to the power of x in blue and y equals 3 to the power of x in green, y equals e to the power of x is really close to 3 to the power of x because base e is like 2 point something. It's like 2.723 blah 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 blah. It's really close to 3. So that's why this graph is close to 3 to the power of x, right? But notice it's between 2 and 3. Okay. So then we're asked to use transformations to sketch this graph. Okay. So say this was the positive y, and say the positive x went in this direction. Okay, so if we just did the general graph, general shape of an exponential, right? So it kind of starts here, it passes through this point, and then kind of goes like that. So the transformations that's going on here, if we work our way from the inside to the out, we have a -1 on the inside. So that says that take the original graph and move it to the right by 1 unit, and then that +2 tells us to go up by 2 units, right? Those are the two transformations that's going on. So if we follow the point of 0, 1, if we go right 1 and up 2, that's going to be the graph, our final graph, right? And we still have this asymptote going on. We have this horizontal asymptote, okay? Right. So that was, again, this is just a rough sketch, but that's just applying the transformations. So you can see the final result in red here. 1 unit to the right and 2 units up. So then say we want to do a model for exponential growth or decay. So this is the exponential growth model where A of t is going to be the amount after some given amount of time t. A naught is going to be the initial amount. So when we start, whatever amount we start with. K is going to be our growth rate if K is positive, and it's our decay rate if K is negative. And T is going to be our time. So this is where we might move away from time in years, right? But when we're doing the money, we usually do that one in years. Okay. So in the year 2000, the human population of the world was approximately 6 billion, and the annual rate of growth was about 2.1%. Using the model on the previous slide, estimate the population of the world in the following years, right? So we have an exponential model, which is A of t is going to be A naught times e to the kt. So then for A, let me see, if 2000 is going to represent year 0, and we want to know what happens in 2030 based on the model, then that means we're going to find A of 30 years later, after 2000. That's going to be the initial amount. So in 2000, the population was 6 billion times e to the power of, the growth rate was 2.1%. So we're going to say 0.021. And the time has been 30 years. Okay. So then here, we're going to say 6 times e to the power of 0.021 times 30. So we get about 11.27 billion people. And then for part B, if we want 1990, that's going to be A of negative 10. So it's going to be 6 times e to the power of 0.021 times negative 10. All right, so we can call them the same function, but now instead of 30, we're going to do negative 10. Approximately 4.86 billion, based on the model. All right. So we got this result, and we got this result. Okay. So we see here, so the predicted, oh no. Okay. And then, so based on the model, they were saying in 1990 it was about 4.86 billion. The actual population at that time was 1990. Okay. Hey, I'm streaming, just so you know. Yeah. So stop! Don't come in here, she's not gonna come in. Okay. Let's see. Oh, I keep forgetting about this one, right? So I didn't mean to show the result, but the result is showing. So we buy a boat for 22,000. The boat depreciates at a rate of 15% of its value. Find the depreciated value. We're essentially doing the same thing, but our formula now, instead of being a positive KT, is going to be negative KT for exponential decay. But otherwise, everything else is the same. The starting amount was 22,000. The decay rate was 15%, so as a decimal was 0.15. The time was 5 years, and we just plug it into the exponential decay model. Again, we have a negative exponent. And so you just want to make sure you can use your calculator properly here. Yeah. We had to express the rate as a decimal. So if it's 15%, we're dividing by 100, so we move the decimal 2 places to the left. Yeah. Yep. Okay, I think this closed out section 3.1. I'm going to go ahead and load section 6.4. So give me a moment to kind of like update.